All right, so for our lesson today, we'll be discussing the second part of the solutions to non-homogeneous linear ordinary differential equations of order n using the variation of parameters. So for this time, we will have the variation of parameters. So just to recall, there are two types. This one is for our case one, basically where the r of x is equal to 0, that is homogeneous. However, for when r of x is not equal to 0, this is the second case or the second type. And then for the second type, for the non-homogeneous, you know that your solution would take the form of y is equal to yc, or the complementary solution, plus the yp, or the particular solution. So the complementary solution, it's actually the general solution of the homogeneous linear differential equation. So if you can recall this one, your yc, based on the four types before that we took in the homogeneous ones, you can have either, what's the first type or first case, guys? Real and distinct roots. And then the second case is real but repeating roots. The third case is imaginary roots. The last is imaginary and repeating roots. So those are the four cases that we had. So we will still be using the knowledge and the concepts that we have learned from that to our lesson today. So we're in. So it's here, C1, C2, C3, and so on, are arbitrary constants. However, YP, or the particular solution, it depends. Where does it depend? It depends on the form of your complementary solution. I'll show this to you. For variation of parameters, let's just say that your complementary solution takes this form: C1, F1 of x, C2, F2 of x, and so on. Your particular solution would be function of x, any function of x, times F1 of x, any function of x, F2 of x, and so on. So C1, instead of just C1, C2, up to Cn, which are purely constants, you replace them with C1 of x, or with me personally, instead of like writing C1 of x, I write letter A, letter B, letter C, and so on. Take note that Rx here for variation of parameters, how do you know when to apply variation of parameters? Rx is not a particular solution of some homogeneous linear DE with constant coefficient. Whereas in method of undetermined coefficient, you know that the Rx is actually solution of, the normal solution where we can derive. Here, let's go to some examples. For example, y double prime plus y is equal to tangent of x. So how, some of you might say, isn't it that this one is simple and can be solved by the method of undetermined coefficients? No, because for method of undetermined coefficients, the right side should be either solutions of real distinct, real repeated, imaginary, or imaginary repeated. It could work if this is possibly sine x or cosine x, but not tangent x. This one could work if this is sine or cosine, but not secant. And then in here, you'd say, oh, that's E. That's possibly real. Yes, but then it has a denominator. So if it's only e to the 2x, you can use a method of undetermined coefficients. But since there's 1 plus e to the 2x at the bottom, you cannot use it. All right, so let's try. The first one, y double prime plus y is equal to tangent of x. So how do we solve something like this? Let's go step number 1. Solve for yc. How do we solve for this? First, we have to set f of m is equal to 0. All right, so how do we do that? We can see that this one is the second derivative of y, or second differential, plus this one is simply y is equal to tangent of x. And then we factor this out. So look at this one. You would want to have f of m is equal to 0. So that means we will not look at the tangent x anymore. So this one, we would want to make it f of m. Isn't it that this one could be written as m squared plus 1 is equal to tangent of x? But then we would want f of m to be 0. So here, m squared plus 1 is equal to 0. Because we would want f of m to be 0. So let's solve. M would have plus and minus I as the roots. Therefore, if it's plus and minus I, A is 0, B is 1. Can you give me the complementary solution for this, guys? And these are the roots. What? Some of you might write e to the 0x c1 cosine of x plus c2 sine of x. Am I correct? And then, since that's e to the 0, that's equal to 1, I can just say c1 cosine of x plus c2 sine of x. This one's quite easy because this one is the homogeneous part. All right. Step number 2, what we do is we propose YP. However, you have to take note that your YP is similar in form to your Y sub C. However, C1, C2, C3, and so on up to C of n would be replaced to, would be in the form of A, B, and so on up to Z, where they are functions of x, because these ones are constants. So if I would propose a YP, I can say that my YP would then be A cosine of x plus B sine of x. However, we have to take note that A, B, and so on are functions of x. All right, looking at the original question, you can see here there's a y double prime. Since a y double prime, what I need to have is, first, I need to have a y prime of p. Take note that A and B are both, here A is a function of x, and B is also a function of x. So when we get the derivative of this one, it has to be the product rule. Derivative of the first, copy the second, derivative of the second, and copy the first. So it becomes minus plus b prime sine of x plus b cosine of x. And then what's going to happen here is that I need a double prime. However, when I solve for the double prime, it would be difficult to have this line, because look at this line. This line contains an A prime already and a B prime. So what I do here is, I would say, let those with prime, A prime, cosine of x, plus B prime, sine of x, be equal to 0. Some of you might ask, so if that is equal to 0, that means my y prime p let's just call this the new one. It would just then be negative a sine of x plus b cosine of x. Since I assumed or I left the a prime cosine x plus b prime sine x to be 0, I can just remove those with primes here. And then whatever's not prime will be left. So this is an assumption. All right. As I said, what I need is a y double prime because the question is a y double prime. So y double prime of p is negative a prime sine x minus a cosine of x plus b prime cosine of x minus b sine of x. So now I have a y of p, the new y prime of p, and the y double prime of p. So what do I do with them? What I do here is take note that y double prime in the original question plus y is equal to tangent of x. So I can say that y double prime of p plus y of p can be equated to tangent of x so that I can solve for the a prime, the b prime, and eventually a and b. So let's rewrite this first. So what is here? What is y double prime of p, guys? It's, I'll change color. Negative a prime sine of x minus a cosine of x plus b prime cos x minus b sine of x. And what is y of p? The yp is there, the one on top. A cosine of x plus b sine of x. A cos x plus b sine of x. And then as I said earlier, note that y double prime plus y is equal to tangent of x. So here, I replace everything with the y double prime. This is actually the y double prime of p, and this is the y of p. So negative a prime sine of x minus a cosine of x plus b prime cosine of x minus b sine of x. The whole thing is your y double prime of p plus the y of p, which is a cosine of x plus b sine of x is equal to tangent of x. So now let's try to simplify what we can simplify and cancel what we can cancel. Negative a cosine of x and a cosine of x cancels out. Negative b, this one cancel out. So that means you're only left with negative a prime sine of x plus b prime cosine of x is equal to tangent of x. So let's just call this equation number 2. And isn't that earlier I gave you an equation number 1? Right? And then your equation number 1, if we can recall, that is here. A prime cosine x plus b prime sine x is equal to 0. So using equation number 1, a prime cosine x plus b prime sine of x is equal to 0. So this was equation number 1. Now, we will use the method of elimination. It's up to us what to eliminate. So if I would say, I would want to eliminate a prime. those with A prime. Can I multiply the top, guys? Can I multiply the top or equation number 2 by cosine? And then I'll multiply the bottom by sine of x. I can, right? Because this one in turn would give me negative A prime sine x cosine of x plus B prime cosine squared of x is equal to tangent is sine over cosine. Multiply to cosine, you're just left with sine of x. And then at the bottom, A prime sine of x cosine of x plus B prime sine squared of x, and then 0 times sine is 0. So in here, we can eliminate the first terms. You're only left with B prime cosine squared x plus B prime sine squared x is equal to sine of x. Isn't it that if I factor out cosine squared x plus sine squared x, what is this equal to, guys? If I factor this out, isn't it that this one, using your Pythagorean identities, that's actually equal to 1? So I can safely say that B prime is simply sine of x. So if B prime is sine of x, I can say that my B integrating this is actually negative cosine of x plus the constant coming from integrating letter B. Some of you might ask, what's constant B? Because I integrated the letter B. Now I have solved for B and B prime. Let's solve for A. So how do I solve for A? So let's just say, so using 1 again, I can say that A prime cosine of x plus, you know that B prime is actually sine x. So sine x is equal to 0. So A prime cos x is actually negative sine squared of x. And isn't it that sine squared of x is sine squared of x is actually 1 minus cosine. So this one becomes cosine squared x minus 1. Therefore, A prime is actually cosine squared x minus 1 all over cosine. So this is simply cosine of x minus secant of x, but that is A prime. What we need is A. How do we solve for A? So A is cosine x minus secant x. Yep. Therefore, A is simply negative sine x minus ln of secant x plus tangent x plus the constant in solving for A. Sorry, that's positive sign. All right. So again, integrating A prime, which is cosine minus secant. Where did I get that from? Here. Cosine x minus secant x, integrating that becomes sine of x minus ln of secant x plus tangent of x plus the constant coming from A. Now, so this is actually what you call your step number 3. 3, it's actually solving for A, B, and so on. And then what's your step number 4? Step number 4, y is equal to yc plus y of p. Now, what is your y of c? Let's go back. Your y of c is here. Here at the bottom. C1 cos x plus C2 sine of x. C1 cos x plus C2 sine of x. And isn't it that, as I said before, the y of p would take the same form as the y sub c? It's just that we replace that with another letter. So a cosine x plus b sine of x. However, what is your a? My a is this one. Okay. C1 cos x plus C2 sine of x plus your a is, so let's rewrite that, sine x cos x minus cos x times ln of secant x plus tangent of x, and then plus c of a. Yes. And then there's b sine of x. What is b? Our b that we solve for is actually negative cosine of x plus cb. So plus negative cosine of x sine of x. And then take note, there was the constant for a and constant for b. There are two constants. Okay, now maybe we can try to cancel if there are things that can be canceled. Sine x times cosine of x, and then this is minus cosine x sine x. These two cancel out. And then take note that these two are simply constants. We already have C1 and C2. So I can just say, let's call this C3. So that finally, my y is actually C1 cosine x plus C2 sine of x minus cosine of x ln of secant x plus tangent of x plus c3. This is your final answer. Actually, I'll introduce to you another technique, which is what you call the using the Wronskian or the determinants. Right? This is actually very useful when we are solving for this one. Useful in solving for A, B, and so on. So let's try to just recall. You know that earlier we had two equations. Your equation number one was A prime cosine of x plus B prime sine of x was equal to 0. And then your equation number two, negative A prime sine x plus B prime cosine x is equal to tangent x. So in here, we would be using the concepts of determinants. However, in order to do that, we need what you call the augmented matrix. So what is an augmented matrix? Let's just say here, the A prime, the B prime, and then in here, what I'll have is the Rx. So in terms of matrices, I'll just write the coefficients of those separated by a vertical line, and this one. So the coefficients of A prime from the first equation is basically cosine of x. Second equation, the coefficient is negative sine of x. For B prime, the coefficient is sine of x, and then at the bottom, it's cosine of x. For the R of x, the top is 0, and then this is tangent of x. And then using determinants, if you have already studied determinants and matrices in high school, D is simply cosine of x, sine of x, negative sine of x, and then cosine of x. So what I do here is, in order to solve for the determinant D, the primary diagonal, which is cosine squared of x, minus the secondary diagonal, negative sine squared of x. So this ends up as cosine squared of x plus sine squared of x, which is equal to 1. So I know that my determinant D is equal to 1. Now, let's solve for A and B. How do you solve for A prime and B prime? A prime, guys, can be solved by this. And then B prime can be solved by... So what do I mean by dA over D, and what do I mean by dB over D? You know what D is. The thing is, what is dA? dA actually, guys, is in place of the column A, you write the constant matrix or the R of X. So 0, tangent of X. But in replace of B prime, it's still the same. So primary diagonal, that's 0, minus sine X, tangent X. So what's this one? I can say that that is negative sine squared X over cosine of X. And isn't it that this one is actually cosine squared X minus 1 all over cosine of X? Am I correct? So that's dA. So if I would simplify the dA, that gives me cosine of X minus secant of X. This is still dA, guys. That's D of A. Therefore, I can say that my A prime is cosine of X minus secant of X all over 1, which is still the same, minus secant of X. And then let's solve for dB. In order to solve for dB, guys, sorry, there. In order to solve for dB, I need to replace the column B by Rx, but column A is still the same. So the first diagonal or primary diagonal, cosine times tangent. So it's just sine of X minus 0. So that means D of B, the determinant dB, is simply sine of X. Therefore, this is sine of X all over 1. The answer is sine of X for B prime, A prime. Isn't it earlier, guys, that our A prime is cosine X minus secant of X, which is this one? And our B prime is sine of X. It's actually this one. So that means you can use the Wronskian or determinants in solving for them. However, this is very prone to mistakes, but this is very useful, especially when you're dealing with systems of equations. Like for a 2 by 2, I would use this. It's okay. But for a 3 by 3 matrix or 4 by 4, the Wronskian is a lot more useful. So this one, in turn, is sine of X minus ln secant X tan X plus constant coming from A. Your B in turn is negative cosine of X plus constant coming from B, which is the same. And your Y is still YC plus YP. So, it's still just the same. Let's go to our next example. All right, guys, can you help me with the steps? What's the first step? Solve for the left side, YC. How do you solve this? By setting Fm is equal to 0, right? Therefore, I can say that m cubed plus m is equal to 0. I'll factor out the m. I'm left with m squared plus 1. So my roots are 0 and plus and minus I. So again, with this, A is 0, B is 1. So guys, can you give me y of c? All right. So this is your assumed yc. Okay. We stop here for the meantime. What's the next step? Propose your yp based on the yc. So replacing, yes, correct. Your yp would then be a plus b cosine of x plus c sine of x. So I used capital C. And then what do I do next? So I need to differentiate. So when I differentiate, this gives me what? It's a prime. Kasi take note that your a, b, capital C are functions of x. Therefore, that's a function of x. A prime plus or minus plus, sige, b prime cos x minus b sine of x, c prime sine of x plus c cos of x. So, andito na naman tayo. So, before we proceed, what can we do, guys? The primes would be equated to 0. So, we'll call this equation number 1. So, I can see that this one, the new y prime, let's just put an asterisk, is negative b sine of x plus c cosine of x. And then we need the double prime because in the question, it's the third derivative. So we're doing the second derivative now. So negative b prime sine of x minus b cosine of x plus c prime cos x minus c sine of x. So guys, this is the y double prime. I still need a y triple prime. And again, I don't want multiple primes with the A, B, C here. What do I do? Can you suggest what to do? Those with primes, let's assume that this is 0. Let's just call this equation number 2, just in case. All right. Therefore, the new y double prime p, the simplified one, is negative b cosine of x minus c sine of x. Now, we will reach the y triple prime because we need to have a y triple prime because of the problem. So it becomes negative b prime cos x plus b sine x minus c prime sine x minus c cos x. Now, I have a y triple prime in here. I have dy because this one is the first derivative. So what I need in the The equation that I'll be writing is this one and this one. Sorry, the new y prime. Okay. So now let's go back to the problem. The problem here is third derivative of y plus the derivative of y is equal to secant x. So that means what I need to have in here is a y triple prime of p plus a y prime of p is equal to secant of x. Now, let us recall, what is your y triple prime? It's here. Negative b prime cosine of x plus b sine x minus c prime sine of x minus c cosine of x plus y prime of p. Oh, you need the original y prime of p, sorry, because this one, for the substitution, you will use the originals. The only reason why I have the new one is because I need to simplify that, right? To be able to get to the next step. But if I ask you, what's the y double prime? It's actually this one, not this one, because this one, the one with asterisks, are the simplified versions. So plus a prime plus b prime cosine x minus b sine x plus c prime sine of x plus c cosine of x is equal to secant of x. And then let's see what we can cancel. If there are things that can be canceled, the b sine x cancels out, the c cosine cancels out, the b prime cancels out, the c prime cancels out. So here, you're only left with the a prime is equal to secant of x. So guys, if a prime is secant of x, what is a? It's ln of secant x plus tangent of x plus constant coming from a. Now that I have my a prime, looking back here, I have my a prime already. So that means using equation number 1, it says here, a prime plus b prime cosine x plus c prime sine x is equal to 0. So a prime plus b prime cosine x plus c prime. But I already know what my a prime is. Therefore, I can say b prime cos x, c prime sine x is basically, all right. And then take note that we have equation number 2. Our equation number 2 is negative b prime sine x plus c prime cosine of x is equal to 0. So guys, look at this. In here, what would you want to cancel out? Me, I'd cancel the b prime because the b prime has different signs already. But I need to multiply this by the whole thing. I need to multiply this by sine of x. I need to multiply the whole thing by cosine of x. Therefore, the new equations would be b prime sine x cos x plus c prime sine squared x. Secant is, what's secant, guys? 1 over cosine, right? So this one is negative tangent of x because negative sine over cosine is negative tangent. This one, negative b prime sine x cos x plus c prime cos squared x is equal to 0. And then if you would combine them, you'd notice that this one cancels out and you'll end up with c prime sine squared x plus c prime cosine squared x is equal to negative tangent of x, leading to c prime is negative tangent of x because sine squared x plus cosine squared x is equal to 1. So I can see here that my c is, what's the integral of negative tangent, guys? ln of cosine of x plus constant coming from c. So that means we can use equation number 2 to solve for b. So here, using equation number 2, I can say here that negative b prime sine of x plus cosine of x times negative tangent of x is 0. So negative b prime sine of x minus this one is sine of x is 0. So negative b prime sine of x is sine of x. So b prime is actually negative 1, or b is negative x plus constant coming from b. This is actually your step number 3. Step 3, solving for A, B, and C. And then lastly, of course, your step number 4, y is equal to yc plus yp. Now, what is your yc? In here, there's your yc, c1, c2, cos x plus c3 sine x. Now, what is your y sub p? Your y sub p is a, but what is your a? You were able to solve for a there. ln secant of x plus tangent of x in here. So I'll just put a star so you can see them immediately, a, b, and c. And then b cosine of x, but what is b? It's negative x. So minus x cosine of x. And then lastly, c sine x, but what is your c? ln. So plus sine of x ln of cosine of x. And then you might ask, what about the small constants? There's a constant for c, constant for a, and constant for b. So I can say plus constant a, constant b, constant c. However, looking at these, I can see that this one, sorry, got erased. These are simply another constant. So C1, C2, C3, I can call this C4. However, purely constant, I can say that C1 plus C4, let's just call that C5. Therefore, your final answer would be C2 cosine of x plus C3 sine of x plus ln of secant x plus tangent of x minus x cos x plus sine of x ln of cosine of x plus c5. So that is your final answer. All right. Again, let's go back. First step, solve for yc, the left side. How do you solve for that? Setting the f of m equals 0. So you know this. This is similar to method of undetermined coefficients. Now that you have the form of the yc, we propose a yp. The particular solution here is again based from this. However, you replace C1, C2, C3 by A, B, and C, the capital C here. So those capital letters are functions of x. So since you have a yp, you need to look at the question. You need a third derivative. So I get my first derivative. Okay, I hope there's no problem here. Now, in order to simplify this, I need to set those primes to 0. Okay, let's call this equation 1. So let's look for the simplified form of the y prime. So it's this one. Based from this, let's solve for the y double prime. Okay, now that I have this, I know that I cannot stop at y double prime because I need a y triple prime based from the question. So that means, again, set those primes to 0. Let's call this equation number 2. Now, the simplified form of y double prime is this one. Based from the simplified form, I can now get my y triple prime, which is this one. Okay, looking back here, the question is y triple prime p plus y prime p is equal to secant x. So I would base those things from the y triple prime here, the one we checked, and the original y prime. So based from the bottom and the one here. Now, try canceling out whatever you can cancel. We're lucky to have simply a prime. It's just secant of x. And then integrating that, that's just ln of secant of x plus tangent of x plus c of a. Now, I know that I still need to solve for b and c. How do I solve for that? Let's look back. Maybe there's equation 1 and 2. Okay. The a prime is with equation number 1. So that means using equation number 1, a prime plus b prime cosine x plus etc. I equated that to 0 earlier. So that means I just transpose this, becomes negative secant x. All right. Now, where do I end? I can't end here because there are still two unknowns, b prime and c prime. I need another equation. So looking back, oh, there's another one. And then I choose to cancel the ones with b prime. Therefore, since they are already inverses or, negatives of each other, I just multiply this by sine of x, the bottom by cosine of x, I'd be able to cancel that and end up having this. So solving this, I'd end up having c prime is equal to negative tangent of x, or simply c is equal to ln of cosine of x plus constant coming from c. Now that I have my a prime and c prime, I need my b prime. What else have I not used? Of course, equation number 2. From equation number 2, here, some of you might ask, sir, can I use equation number 1? It's up to you. But then equation number 1 involves another term. But, I could use equation 1 or 2, but I prefer using 2 because 2 only consists of 2 terms. Now that I have this, what else do I need to do? Okay. Substitute it back because y equals yc plus yp. Here, this is the yc. And then the rest here is the yp, including the CACBCC. And then CACBCC, that's just purely constant. Let's just call it constant 4. And then constant 4 and constant 1, let's just call it constant 5. Some of you might say, can I just call it constant 1? It's okay.